but I am going to, it's just kind of an expansion of what we did before. So the problem was f of x equals the sine cubed of 5x to the fourth plus 7x squared. So the first thing you do, just like we did on the other problems, is you rewrite the sine cubed as the sine, the quantity cubed. So you have sine of 5x to the fourth plus 7x squared, and then you put a parenthesis around it. So the whole thing's cubed. So what you have is you have three parts. You have the inner function, which is 5x to the fourth plus 7x squared. And then you have the next function inside, which is the sine of something. And then you have the whole thing cubed. So there are three parts. Now I'm going to actually just, you may not follow this at the, immediately, but I'm going to tell you what the answer is without going through a long procedure, and just to kind of show you the thought process. So the way you would do this is you would know that you have to take the derivative of this thing that's furthest inside. So you would have 20x cubed plus 14x, okay? So that's the derivative of this thing. And then you would go to the next part inside, which would, the derivative of the sine would be the cosine of 5x to the fourth plus 7x squared. So the derivative of the sine is the cosine, but you don't change the argument. Anytime you take the derivative of a trig function, the argument never changes. And then finally, you would have this whole thing, and again, this part in the inside doesn't change. All you're going to do is use the power rule. So the last part would be 3 times the quantity, the sine of 5x to the fourth plus 7x squared, the whole thing squared. And then this would be multiplied by that. Okay? Okay, so this is kind of the way, if you get good at these things, you don't have to go through the whole U's and U's of things and other things. You go to the most inside part of the composite function, you take the derivative of that. That's the last part. Then you go to the next inner part, which is the sine of something. So the derivative of the sine of something is the cosine of something. And then you go to the outside function, which is this something cubed. So it's 3 is something squared. Okay. So you see how they kind of, when you have something grouped in a parenthesis, you just treat it as a fixed quantity. And then you take the derivative of the outside part. Now I'm going to show you the long way and show you that hopefully I got the right answer here. So the way you would actually do this more formally is you would say that f of v was equal to v cubed. So this whole thing is v. V of u would be equal to the sine, wait a second, is that right? Yep, the sine of u, and u of x would be equal to 5x to the fourth plus 7x squared. So you can see if I plug that into here, I'll get the sine of 5x to the fourth plus 7x squared, and if I plug that into there, I'll get the sine of this whole thing cubed. So now we'll take the derivatives. So f prime of v, what this is the derivative of this expression with respect to v. So that becomes 3v squared. V prime of u is just the cosine of u. And then u prime of x is 20x cubed plus 14x. So the chain rule says that f prime of x is f prime of v times v prime of u times u prime of x. So we just add that one extra term and introduce this variable v that we didn't have before. And you plug those in there. So you get 3v squared times the cosine of u times 20x cubed plus 14x. So that's just the easy plug from our previous step. And then we go back and we first plug in u. So we get 3v squared times the cosine of u. U is 5x to the fourth plus 7x squared. And I already have this part, so I'll leave that on there. And then finally, this is v. I mean, this is not v. This is, where's v? V is the sine of this thing. So you get 3 times v, which is going to be the sine of, plugging u back in here, the sine of 5x to the fourth plus 7x squared. And that whole thing squared times the cosine of 5x to the fourth plus 7x squared times 20x cubed plus 14x. And so that should be the same thing that I got previously. And you can do the same thing if you only have a two-step process, you know, in terms of, do I have to write out u of x? And the only reason I would have you do that for a test is so that I give you partial credit. If you do something in your head and you do it wrong, then I can't give you partial credit. So that's the reason I would probably tell you to do it this way, even if you know how to do it the way I just, you know, doing the whole thing in your head. You just have to make, if you do that, just make sure you do it right. Usually people who feel confident enough to do that probably know what they're doing, but you never know. Okay, so go ahead and turn those in. I'm going to give you a chance to do the rest of them in class if you just happen to not do the rest of them. So. As long as you do. Is that everybody? Yes. Okay, I'll have to take a little bit off. Yeah, this works out a lot better. In the past, I just said, here's the video, watch it. And I think people tend to think, oh, I don't need to watch that thing. But having an assignment, you actually have to do something. So that's part of my new plan. Okay, so let's, so on a scale of 1 to 10, in terms of how confident you feel in this material. Well, that was just thumbs up. So we'll do three levels. We'll do 2 thumbs up, 1 thumbs up, that, or 2 thumbs down. Okay, so how's your confidence look? 1 thumb up, 1 thumb, yeah, pretty good. Give me 2 thumbs up. Yeah, I got about halfway through the test. I got tired. It wasn't too too bad. Relatively speaking, I think you guys have done it in previous years for whatever reason. Just because nobody didn't see, well, I didn't look at all the tests, but it looked like there weren't too many people who just left them blank. That's usually where you really don't do well. You just don't do anything. You have no idea whatsoever. It seemed like people had some idea. Okay, so let's do an example just to show you. Again, one of the things that we do is we find the equation for the tangent line to the curve. So let's just show this actually works. Okay, that's the nice thing about finding tangent lines to equations is you can prove that this thing actually does work. So I decided, I was thinking about this, I think it was when I was going to sleep last night. I tried it, it's funny. So, you know, you get older and you don't sleep as well. So I take 2 Benadryl at night because they're supposed to make you sleepy, okay? And it also helps because I tend to, you know, have some drainage, so it serves 2 purposes. Anyway, so I have to wait for that to kick in. So I usually start thinking about something to do with class because I figured that'll put me to sleep. And at least it's useful time. So I was thinking about what I was going to do today. So let's just do this prop. Find the tangent line. So we'll say find the equation for tangent line at x equals 3.7. We'll see what happens. So this is a composite function. So what we would do, this would be f of x. F of x equals the sine of x. So to do this, we need to use the chain rule. So what we do is we do f of u is the sine of u, and u of x equals x squared plus 2x. And then you take the derivative of each part. By the way, the feeling in physics is not unusual. Like Mr. Graham, I remember when he talks to people first year, he says, you know, after 5 weeks in governor's school, you feel have these feelings because he's been doing it and he knows what people feel. And of course, I've been teaching physics this will be my 8th year. And don't worry, this is a normal feeling. You don't know what's going on at this particular point, or at least you're not as confident as physics. You know, people, I like calculus because it's more straightforward. That's a normal feeling. We're trying to work on that, but I'm not trying to, you know, there's just no way of getting around it. It's just that happens. Okay, so f prime of x would be f prime of u times u prime of x. So we get f prime of u is the cosine of u times u prime of x, which is 2x plus 2. And then you plug u back in. So you'll get the cosine of x squared plus 2x times 2x plus 2. Or put the algebraic part first. Put parentheses here so that I know. If I don't, I would think I'm multiplying cosine of this times 2x plus 2 at the end. Okay, so you take the derivative. Okay. So now what you do is you evaluate the function at the value of x. So we need to find f of 3.7, and it's radians. So that's going to be sine of 3.7 squared plus 2 times 3.7. So I'll get my calculator out. Yeah, how many people have done the homework for this section? Probably nobody, right? First, so you'll get more practice. So hopefully, after you finish the homework, you'll be even more confident. Okay, so what do we get here? Make sure I'm in the right mode, which I'm not, because I've been doing physics. Okay, so the sine of 3.7 squared plus 2 times 3.7 is just 0.784. So that's the value of the function. And then we need to find the value of the derivative. So f prime of 3.7 is going to be 2 times 3.7 plus 2 times the cosine of, you can fit it on your paper, but 3.7 squared plus 2 times 3.7. Okay, let's see what we get there. 2 times 3.7 plus 2 equals times cosine 3.7 squared plus 2 times 3.7. And the slope is negative 5.83. So when we have the value of the function, and well, we have the x value and the value of the function, and we have the derivative, so this is the slope. This is going to be equal to y1. This will be equal to x1. So we have y minus y1, which is 0.784, is equal to negative 5.83 times x minus 3.7. And we just need to put in the slope-intercept form. So we'll have y minus 0.784 is equal to negative 5.83x. And here we get plus 21.59, negative 5.83 times negative 3.7, and then we add 7.784 to both sides. And we get y is equal to negative 5.83x plus 784, 22.37. So that should be the equation for the tangent line to the original curve at x equals 3.7. So we'll see if I did it right or not. We'll find out if I made a mistake. Okay, so my original function was the sine of x squared plus 2x, I think. Sine of x squared plus 2x. Okay, let's see what that function looks like before we go any further. So we graph that. So it looks like that. That's interesting curve, isn't it? So let's zoom out in the x direction, see what it looks like. So you can see as x gets larger, it oscillates more quickly. It's interesting how it's not symmetric. Anyway, I guess it is symmetric. It's symmetric around this point, almost, maybe. It's hard to tell. I'm not sure if it's exactly symmetric. Okay, so now we need the equation for the tangent line, which is negative 5.83x negative 5.83x plus 22.37, and 3.7 is about here. So let's graph it. And there's my graph. And you can see if I zoom in on this little area, oh, well, it's because I rounded off. Okay, so you can see the effect of round off error here. So it's not quite exactly. I have to take it out to a couple more decimal points to make it actually be tangent, but it's pretty close, right? I'd say I didn't mess up. Okay. So it does work. All this chain rule stuff does work. It does give me the slope of the tangent line. And so that's good. Okay. So we're not going to do any more of those today. We're going to actually move on to the next section. We may come back to it if we need to get some more practice, but right now I'm just going to let you get some practice doing the homework and then. Okay. So the next thing we're going to talk about is what's called implicit differentiation. So what have we been doing? We've been doing what's called explicit differentiation. So if you have an explicit equation, that means you have y equals some function of x. Examples of implicit equations are, and notice I didn't say functions, I said equations. Examples of implicit equations that we probably have seen before are something like that. So does anybody know what that is an equation for? Circle with a radius of? Right. Yeah. So it's a circle of radius 3. And if we draw a circle of radius 3, so here's circle, radius 3. Is that a function? No. Somebody said no. That's not an answer. Why is it not a function? What is the test we use for determining whether something's a function? Yeah, vertical line test. So you can see that if I draw a vertical line here, I intersect the curve at 2 places, so it's not a function. So it's an implicit equation, it's an implicit relationship, and it's implicit because I haven't solved specifically for y. But you're saying, like, yeah, I can solve for y. Let me do that. Let me solve for y. So you'd say y squared is equal to 9 minus x squared, and I'll take the square root, and I get the square root of 9 minus x squared. So that's a function, right? If I plot that. So what did I've done something wrong here. I've left something out on my last step. Yeah. So you have to, when you take the square root, you're supposed to have both the positive and negative. So there actually are two there's plus the square root and there's minus the square root. And if I plot this, the top part would be this part, the one up here, which is a function, and the bottom part is this one. This one here is the bottom part, and that's a function. So these are both functions, but by themselves they don't represent this exactly. They only represent half of the curve. But if I said, are there tangent lines to this curve? I'd say, yeah. I mean, here's a line that's tangent to the curve here, and here's a line that's tangent to the curve there. There's actually 2 places that, this curve is tangent at this point, and it's also tangent to over here, right across from it on the opposite side. So obviously, you can have tangent lines to the curve. So can we take the original equation and find the derivative, dy dx, which is the slope of the tangent line? And the answer is yes. And that's what implicit differentiation does. It allows us to find the slope of the tangent line to curves that are not just functions. implicit equations are, well, I don't know if that's actually true. Yeah, I guess most of the implicit, I can't think of any that are not functions. Okay. Oh, so this is, yeah, this is an extra information here. So, as I said, an example of an explicit equation is y equals x squared plus 3x plus 1, which is a quadratic equation or a parabola. Implicit is a circle or any ellipses, hyperbolas, all kinds of other different ones. This was just to introduce you to another kind of equation that we're going to get to in the second semester, which is called a parametric equation. So this is an example. These are examples of parametric equations, and that's what we're doing in physics when we talk about the x and y directions. The x position is v times t, and the y position is v0 t plus 1/2 at squared. And those are, the t is the parameter. We haven't done that before. And if you go into your calculator, so pull out your calculator. You've got it here. Actually, let me put up the document camera here. Turn it on, that would help. Which Martha would like it, but I wouldn't. But it's called wind plot. And if you go to, say, two-dimensional plots, in terms of your equations, you have four choices. You have explicit, which is what we normally do, parametric, which I just talked about, implicit, and polar. So let's pick implicit. And what they have is x times x plus y times y, x squared plus y squared equals 13. I'm going to pick x squared plus y squared equals 4. So that should give me a circle of radius 4. And you can have programs that plot implicit equations. Now the other one, let's see if I can try this one. X squared y plus y squared x equals -2. Do a new one. So x, what was the function? I've already forgotten. X squared y. So x, y, and y squared x, so put an x on the end there. Oops, rats. Let's try it again. Plus yx equals -2. So that's what that looks like. Okay. Obviously, there are tangent lines to this curve. So they do exist. Okay, let's get into the nitty-gritty details here. We'll come back to that. And let's see. Yeah, let's do it this way. So let's look at what I'm going to do is demonstrate what we do, what we have been doing, but kind of go into a little extra detail. So if we have the function x squared, you don't need to use chain rule with that. But I'm going to use the chain rule just to show you how this works. So what we'd have is that f of u would be u squared, and u would be equal to x. So we normally take the derivative of x, you get 1. So then when you multiply this times that, you get 2u, but u is x, so you get the answer we expect. But the reason I'm doing this is when we take this derivative of u, we're taking the derivative of u, with u prime of x is the derivative of u, which is this, with respect to x. And the variable that I'm taking the derivative with respect to is x. So the derivative of x with respect to x is 1. And when I plug it in, into the chain rule, I get 2x, which is what I normally get. Now, over here, I have f of y. So the function, the thing I'm taking the derivative of is not a function of x, but is a function of y. So what I want to do is the same kind of deal. I'm going to use the chain rule. F of u is still u squared, but instead of this u being a function of x, u is actually a function of y. So when I take the derivative, and I'm taking the derivative here with respect to x. If I took the derivative with respect to y, it would be 1, but I'm taking the derivative with respect to x. So when I take the derivative with respect to x, instead of getting, in this case, dx, because it's the same thing, it becomes 1, you take its dy dx. So I get y prime instead. dy dx is y prime. So then when I stick it into the chain rule, what I get is that f prime, this is f prime of x. So I'm taking the derivative with respect to x. I have the derivative of this with respect to u, and because this is u and the derivative is with respect to u, I use the same rules that I normally use. But this little extra bit, y, when I take the derivative of y with respect to x, instead of thinking I get 1, because the variables are different, I actually get y prime, the definition of the derivative. So when I have an implicit differentiation, basically what happens is I take the derivative of the other variable y as I normally would, using the same rules, but I multiply by y prime to reflect that it's implicit differentiation. Okay, so let me just give you a couple of examples of how that works. And I don't have to go through the chain rule. I use the chain rule to point out why you end up with this extra y prime in your equation. So let's say that I want to, it's not really f of y, but let's say I want to take the derivative with respect to x of, let's say, 3y to the fourth. That's going to be equal to 12y cubed times y prime. If I want to take the derivative with respect to x of the sine of y, that's equal to the cosine of y times y prime. What else do I know? I want to take the derivative with respect to x of the sine of, let's say, the cosine of y. The cosine of y, that's equal to the negative the sine of y times y prime. So that's pretty much it as far as implicit differentiation. That's not at all, but that's the gist behind it. Anytime that you have an equation that you're taking the derivative with respect to x, so we're taking the derivative of every term with respect to x. The ones that involve x, we just do the normal stuff that we've learned. Any term that involves y, then we do it normally, use the normal rules, but we add on the y prime. So let's look at the example the circle example. So the circle example was x squared plus y squared equals 9, let's say. So I'm not going to explicitly solve for y. What I'm going to do is I'm going to take the derivative with respect to x of this whole expression. So that means I take the derivative with respect to x of x squared. I take the derivative with respect to x of y squared, and that's equal to the derivative with respect to x of 9. So it's kind of like what you do when you normally are fooling with functions or equations. If you do the same thing to every term, then the equality remains the same. If we had that original equation, we multiplied everything by 3, 3x squared plus 3y squared equals 27. It's the same relationship. It doesn't get changed by multiplying everything by a constant. And the same thing's true when you take the derivative. If the original equation is valid, then the derivative of the original equation is valid as well. And so, when you take the derivative of this with respect to x, you get 2x. When you take the derivative of this with respect to x, you get 2y, but you multiply by y prime. And then the derivative of a constant is 0. So that's the derivative part. So to find the what the slope is, what is the derivative, or what is the slope of the tangent line, what we do is we solve for y prime, because that is the slope of the tangent line. So you would get 2y, y prime is equal to negative 2x, and divide by 2y, so you get y prime is equal to negative 2x divided by 2y, or negative x divided by y. So that is now the answer. The complicating factor is that you need to know both x and y to figure out what the derivative is. But it still works. And usually you know what x and y are anyway, because you have a curve. So to be able to plot a curve, you have to know what x and y are. So it's not really that much of a big deal. So let's just draw a circle of radius 3 and see if this makes sense or not. See if it actually does what it's supposed to do. So we're going to pick out a few points. We're going to make up a table which is going to be, we're going to plot x and y and then the slope. Let's see what happens. We'll pick the easy ones first. Okay, so x, y, y prime. So one point is 3 comma 0. That's this point. One point is 0 comma 3, which is this point. Then you have negative 3 comma 0, which is this point. And then you have 0, negative 3. So those are the points that are on the curve. And y prime is negative x over y. So in this case, x over y this is undefined, because you'll get negative 3 over 0. This one is 0, because you'll get 0 over 3, or negative 0 over 3. This one is undefined again. You get negative 3 over 0. And this is 0. It's negative 0 over negative 3. Now there's another point, let's say right here at 45 degrees. This point is going to be equal to 3 times the square root of 2 over 2. So let me find my calculator. So if I take 3 times the square root of 2 divided by 2, that point midway from here to here is going to be 2.1213 and 2.1213. So those are the x and y values at this point right there. So I also have one at negative 2.1213 and positive 2.1213. That would be this point right there. So if you plug those in, what you end up with is negative the ratio of those two. Well, they're the same thing. So you end up with the negative 1. And here you're going to have negative, it's going to cancel out with one of those negatives, and you end up with positive 1. So here are the tangent lines. Let's draw the tangent lines. So those are the first four points. So at x equals 3, y equals 0, the slope is undefined, which is true. It's vertical. At x equals negative 3, y equals 0, it's undefined, vertical. At x equals 0, y equals 3, 0. At x equals 0, y equals negative 3, it's 0. So all these are confirmed by the result that we got there. And then the other 2 points on the curve, the tangent lines are going to be like this and like that. I'll move them in just a second here. They're diagonals. So this slope here is negative 1, which makes sense. And this one is positive 1, which makes sense. So we did ones that are easy to verify, but if you picked any point on this circle and you plugged in the x and y values into the equation for the slope, the derivative, it would exactly be tangent to the circle. So it does work for this simple case. It doesn't work always. So we'll look at some more examples on Monday, but I'm not going to assign any homework from this yet, so we'll wait till Monday. We'll stay in here for physics. So we'll see you at 9:15.